A substitution reaction can only occur with saturated compounds. A saturated hydrocarbon is one where all of the bonds between carbon atoms are single bonds. This means that the molecule is going to be full of hydrogen atoms. It has as many hydrogens as it can possibly hold. If I had a double or a triple bond between carbon atoms, then that bond could be broken and I could fit in more hydrogen atoms. So when we're dealing with substitution reactions, we're only going to be using alkanes, all single bonded. If we have alkenes or alkynes, that's going to do an addition reaction. So here I have a molecule of propane. Prop because there are 3 carbon atoms, ane because it's all single bonded, so it is an alkane. The 2 substitution reactions we're going to deal with would be halogens with an alkane, is the first one. Now, a halogen can replace any hydrogen. So if we're going to do a substitution reaction, we're going to take the halogen and we're going to break it in half. Remember, those halogens are diatomic molecules. So let's say this is bromine. I have 2 bromines bonded together. It's going to break apart, and the one bromine is going to replace any one of the hydrogen atoms that's here. So we're going to take the molecule, we're going to pick a random hydrogen atom and replace it with the bromine. So we have one of the hydrogen atoms that has been replaced with the bromine, and then the other hydrogen is going to attach to the remaining bromine. So this is working kind of like a double replacement reaction, except it's specifically with halogens and alkanes. Now, if you notice, I just happened to pick this hydrogen because it was closest to me. But if I had picked this hydrogen, I would have exactly the same thing. If I had picked the back hydrogen, I would have exactly the same thing. Remember, these molecules are constantly moving. So any of the 3 hydrogens on the end carbon is going to be the same molecule because this is rotating through all of those positions. Likewise, if I had picked a hydrogen on the other end, well, that's just the molecule flipped over and rotated. So any of these 6 hydrogens are going to produce that same molecule. So when we go to name a hydrocarbon that it's not a hydrocarbon anymore because now it has a halogen on it, that's called a halide or a halocarbon, we're going to name that halogen just like we would a carbon branch. So instead of methyl or ethyl, based on how many carbons are coming off of the branch, Br would be a bromo group. So this would be 1 bromopropane. And so would this, and this, and this. We don't specify where in that rotation it is because all 3 of those are the same. And if I had put it on this side, still 1 bromopropane. However, that's not the only compound I can produce. I could also put the bromine on one of those 2 hydrogens, and that would produce something different. So instead of putting it on here, if I had picked the middle carbon, I would end up with 2 bromopropane. So when I go to do this replacement reaction, I just pick any hydrogen that's there, pop it off, and pop one of the halogens on. So if we're going to draw this out with our structural formulas, here is my propane, here is my bromine. I'm going to pick a hydrogen. I'm going to pick this one this time. I'm going to pop that off, and I'm going to switch it with the bromine. So up here, this becomes bromine, and this becomes hydrogen. Now, the bromine does have 3 lone pairs around it in both spots here, but quite often when we're dealing with organic molecules, we kind of simplify things a little bit and leave those lone pairs off just because it gives us so much more to look at and can make things a little bit more confusing. So pick a hydrogen, so write the reactant, pick a hydrogen, erase it, and replace it with the halogen. So again, there's a couple different products we could have, and whether I put it here, 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 or here, it's producing that same product, but here and here would be a different product, but the top and bottom would both be the same. The other one that I can do is I can replace any halogen with an OH group. So here I have something with an OH, so that something's going to pop off. I have that OH minus ion. The only thing the OH can replace is a halogen. So I cannot take off just any random atom that I want to. The only one that I can take off is the halogen. So because the halogen is here, I can pop the halogen off and pop on an OH right there. This is the only product that I can produce. I can't put it anywhere else because the OH can only replace a halogen. When I have this little OH group on here, that's called an alcohol. And an alcohol, the ending actually changes. We don't name this like a branch. We change the ending. Alcohols end in the anol suffix, but we do still give a number saying where that OH group is. So this is coming off of carbon 1, 2, or 1, 2. It's coming off of carbon number 2. So this would be 2-prop because there's 3 carbons, and then it would end in anol because of that OH group coming off of it. This is actually rubbing alcohol, the structure for it. So again, if we were to try and draw this out, we have a halocarbon. It has a halogen right there. We have something with an OH group. We're not going to worry about what it's attached to, but that OH would switch with the halogen. And we would end up with the OH in wherever the halogen was. So this had the halogen on carbon number 1, so the OH group goes on carbon number 1. So this would actually be 1-propanol. So again, when you have a halogen replacing a hydrogen, it can replace whatever hydrogen you want, and there are multiple products that can form. When you're replacing a halogen with an OH, that OH can only replace the halogen, so wherever that halogen is gets picked off, and an OH would go in its place.